if and only if it has the strict order property or the independence property. So you get a dichotomy theorem of the following kind. If you have lots of types, then either you have a family of types which is highly structured in the sense that all the types come from cuts, or it's not structured in the sense that it's completely random. You have the independence property. It's a remarkable theorem, and what's more remarkable is that he proves it twice. So in chapter 3 of classification theory, he proves the following. A theory is not simple if and only if it has either the tree property of the first kind or the tree property of the second kind. This isn't the language he used to prove this theorem. But this says that if you have a lot of forking, then either you have a lot of forking which is highly structured or highly random. TP2 is the random case, and tree property of the first kind is the structured case. And the basic object of study is the classes of theory which don't have the tree property of the first kind. OK, so what is the tree property of the first kind? So to start with, let's talk about what the tree property is. So we have a formula phi xy where x and y can be tuples. And we say phi has the tree property. There's some tree of tuples, by which I mean just a collection of tuples in some model, indexed by a tree, and a number k, such that paths are consistent. So if I choose any path in omega to the omega, and I instantiate my formula along tuples indexed by that path, then I get a consistent type. And if I fix a node, so eta here, and I look at all of its children, all of the descendants of that common node, then I get a k inconsistent family of formulas. OK, so what does this look like? So here we've got a tree. So paths are consistent. But if I pick a particular node, like this blue guy here, then I get something which is k inconsistent. There are going to be a lot of pictures in this talk. OK, so this is the tree property. It's a familiar thing. And a theory is simple if and only if it doesn't have the tree property, if and only if forking satisfies local character. You can think of the tree property as a witness to the failure of local character, because it is a lot of dividing. And what does local character say? It's a kind of compactness phenomenon. It says that regardless of how big my type is, I can always find some subset of it, uniformly bounded by this cardinal kappa of t, which is less than or equal to the successor of the size of the language, such that the type of a over b doesn't fork over this small subset. So all the essential information about a is contained in this small subset. OK, so the tree property, its negation characterizes simplicity. What is the tree property of the first kind? Again, for a formula, we have a tree of tuples, and we have the same consistency condition. So paths are consistent. But now our inconsistency condition is strengthened. It says that any two incomparable elements give me an inconsistent set of formulas. So again, paths are consistent. But now if I choose any two incomparables, which don't have to be children of a common node, I get something inconsistent. And so if you think about the tree property, it said that if I picked a particular node, and I looked at all of its descendants, I got something k inconsistent. That's agnostic about what happens between elements that aren't in that configuration. So the tree property of the first kind says that anything which isn't forced to be consistent in the definition of the tree property is inconsistent. The tree property of the second kind says that anything which isn't forced to be inconsistent by the tree property of the second kind, by the tree property, is consistent. So it's two extremes.
So far you defined the first kind. You didn't do the second kind.
I didn't define the second kind, and I'm not going to. But
why not?
Well,
so say just for the audience.
Yeah.
I mean, say the second kind.
Yeah, OK. So the tree property of the second kind looks like this. So I've got a formula. And now I have an array, aij, I, j less than omega. And the consistency condition says that if I have a function from omega to the omega, then if I let my function pick an element out of each row, I get something consistent. And if I fix a row, and I let j vary, this is k inconsistent. OK, so this is phi has TP2. OK. All right, so that's the picture. What did I? Oh, yeah, so in TP2 is when you don't have that. Good. OK, so yeah, so some word on terminology. Sometimes people say SOP2 instead of TP1. They're equivalent in a strong way. So how do I get SOP2? I just replaced omega to less than omega by 2 to less than omega everywhere. But an easy compactness argument shows that these two things are equivalent, even at the level of formulas. So I'll use them interchangeably. And Kim and Kim have shown that if you replace 2 by a weaker condition that say any k pairwise incomparable elements are inconsistent, that will give you.
What do you mean Kim and Kim?
Well, there are 2 people with the last name Kim that wrote a paper. They proved this result. Yeah.
Oh, I see. So
More than one person with name Kim.
Yeah.
Way more.
it's Kim Il-sung.
Okay. Well. Okay. So 2 people proved this theorem. Okay. So some examples. So here's some easy examples. So DLO obviously is the true property of the first kind. You can build it by hand, looking at nested intervals. And slightly harder to see, but still easy, is the triangle-free random graph. This is an NSOP theory, but it has SOP3. And from there, it's easy to check that you have true property of the first kind. And we have the following implication. So we know that simple theories are contained in the theories without the true property of the first kind, which is the same thing as NSOP2 by that remark. Now, we know that every theory which doesn't have the true property of the second kind also doesn't have the stronger order property 3. But these might be distinct. We don't know yet. It's open. And then, this continues on through the SOPN hierarchy, and then you have SOP. Okay, so these are known implications. Okay, so here's what we're up to, broadly speaking. So the true property of the first kind is it's an important dividing line. So one major result that we know about it is this result of Granger and Shelah, where they prove that TP1 characterizes maximality in the interpretability order triangle star. This was studied by Džamonja and Shelah. Assuming some mild set-theoretic hypothesis. And it conjecturally characterizes maximality in Kiesler's order, so we have some very sort of canonical outside definition, which seems to pick out exactly the kind of complexity that the true property of the first kind measures. But there's some problems. So one of them is that it's beset by problems even at the level of syntax. So there are several different definitions of properties in the neighborhood. We don't know how to separate them. And that seems to be a problem. So even before you can start doing real model theory, you're sort of beset by a family of syntactic problems. So the second problem is that we don't know how it connects to other natural model-theoretic notions. If we want to think of looking at theories without the true property of the first kind as a generalization of simplicity, it should have something to say about forking or amalgamation of types. And nothing like that had been looked at. And third, we need a sort of better stock of examples. So the plan for the talk is to sort of talk about progress in each one of these 3 areas. To talk about some syntactic questions, to talk about amalgamation of types, and then finally to talk about how our work in amalgamation of types gives us a new stock of examples of new theories in this class. Okay, so let me talk about another property in the neighborhood called weak KTP1. So if I have k elements of my tree, I'll call them a collection of distant siblings if any 2 of them will have the same meat. So this is like a delta system for the tree. Okay, so a formula has weak KTP1. Again, paths are consistent, but now my inconsistency condition says that I get inconsistency only when I have k distant siblings. So this is a weaker, in principle, inconsistency condition. So what does it look like? So again, paths are consistent, and here's a picture where I have 3 distant siblings. Because if I take any 2 of them, their meat is this blue. Okay. All right. So it's easy to see that weak 2 TP1 is the same thing as TP1, because any 2-element set, it's a collection of 2 distant siblings. Okay, so these 2 things are the same. That's an easy equivalence. And it's also clear that if I have weak 2 TP1, then I have weak 3 TP1 and weak 4 TP1. And so you can ask the question, erase this if you don't like Kim and Kim. Is weak KTP1 equivalent to TP1 for all k greater than or equal to 2? It's a natural question.
So what did Kim and Kim prove? I thought it was the same.
No, so they prove that if you choose k pairwise incomparable elements. So this has an additional assumption that they're distant siblings, that they all have the common meat. Okay. Yeah, so you can ask this question, is it equivalent for all k greater than or equal to 2? Okay. So we'll settle this using some strongly indiscernible tree arguments. So I should tell you what a strongly indiscernible tree is. So we work with the following language on the index model. So I'm going to have the tree partial order, a lexicographic order, and the binary meat function. And I can view the tree kappa less than lambda for infinite cardinals kappa and lambda, or kappa could be 2. That's fine too, as an L naught structure in a natural way. So I interpret this as the tree partial order, this is the lexicographic order, and the binary mean function. OK, so if I have a collection of tuples indexed by this tree, I call it a strongly indiscernible tree over C if whenever I have a collection of tuples from my tree and their quantifier-free types are the same with respect to this language, then actually the types are the same. The elements that they index end up having the same type over C. OK, so Takeuchi and Tsuboi proved that if you have the tree property of the first kind, or even weak KTP1 for some k, then that'll be witnessed by a strongly indiscernible tree. And the reason that this is useful, or at least one reason it's useful, is that it lets you linearize the problem. Instead of working with the tree, you can work with a single path. So if you have a strongly indiscernible tree, and there's some path which is consistent, and there are two incomparable elements somewhere in your tree which give you something inconsistent, then you have a witness to the tree property of the first kind. Why? Well, because if you have a strongly indiscernible tree, then any two paths have the same type. And any two incomparable elements will have the same type, provided you list the lexicographically least one first. Okay? So any two incomparable elements will give you an inconsistency if one pair of them does. Any path will give you something consistent if one of them does. So this is a very helpful reduction in the problem. And the main lemma that goes into the things we do is this lemma we call the path collapse lemma. So what this says is the following. So I fix a strongly indiscernible tree. Eta, and omega is less than kappa. And it's indiscernible over C, but also if I look at just the all zeros path, it's indiscernible not just over C, but over some little element C. And I look at the type of this little element over the all zeros path. Then I can sort of switch the parameters here to the path that starts with 1 and then continues with all zeros. And I can ask, do these two types, are they consistent? Well, what our lemma will say is that if this isn't consistent, then you have the tree property of the first kind witnessed by some formula in one of these types. And this is often most useful in its contrapositive form. So it says that if you don't have the tree property of the first kind in the formula witnessed from these variables, then in fact you can push these types together. So I'm going to prove this in a kind of movie. So we start with a strongly indiscernible tree, right? And then
maybe to say what the lemma again is. I mean,
yeah, sorry.
So in the drawing.
What?
In the drawing is better.
OK, so you want the drawing first, and then I can come back?
Just say what the lemma says.
Yeah. No, I'm doing that. I'm getting there. Yeah. So it'll be a sequence of slides which sort of explain what the lemma say. So we start with a strongly indiscernible tree. So remember, this is indiscernible over some set C. And we restrict attention to two paths. So this is going to be the all zeros path here. And this is the path that starts with 1 and then continues with all zeros. And remember, this type is going to be the type of little c over the all zeros path. So I'll go back and how do I go back? OK, yeah, so the green type here is going to be the type of c over the all zeros path. So it looks like this. OK, so this is consistent because it's realized. It's realized by this little c. But our assumption is that, let's say, that these two types together are inconsistent. So this is the type of C when I replace the parameters with this path, and I take the two of them together. Well, then by compactness, there's going to be some finite initial segment to the two paths, which gives you the inconsistency. And then what do? You just build a tree out of these elongated pieces. You build the tree out of these sort of initial segments.
Wait, the tree have height kappa, large kappa.
That's right. So it's infinite.
So
That's
initial segments.
well, because by compactness, that these two paths were inconsistent. So so it's indiscernible. So
Right.
yeah, so you use that. So it's indiscernible if it's little element c. So you know that there's going to be some finite subset somewhere, but then you can slide it down using indiscernibility. Yeah. OK. So this is what we call the path collapse lemma. And it has the two applications. So the first application is that a theory has weak KTP1.
Wait, what was the
Oh yeah. Sorry, you wanted me to go back. OK. So there was the movie, and here's the statement. Yeah. So it says that if I look at these two types, if I don't have TP1, then I can collapse them and put them together. All right. So now I'll say the applications. Okay. So the first application is that a theory has weak KTP1 if it only has TP1. So how do you do this? Well, you know that. So suppose you have KTP1. Then if I look at the paths indexed, so I look at the all zeros path and the path that goes 1 and then all zeros, the path that goes 2 and then all zeros. I know that these can't all be consistent, because these first elements in particular are going to form a family of distant siblings. They all meet the empty set, the empty node. So I can't collapse paths forever. And just iterating the application of the lemma, or fattening the tree, you can prove this fairly straightforwardly from that. Somewhat more difficult is the following. So if you have a theory with the trait property of the first kind, you can witness this using a formula in a single free variable. And this, you sort of have to use infinitely many applications of the path collapse lemma. So you start with a binary tree, you collapse, and that lets you go deeper and deeper into the tree. So working with iterated fattenings of the tree, you can realize one of the variables across the whole tree, and you reduce the number of variables in your witness to the trait property of the first kind. So I won't go into the details, but this also, it uses the path collapse lemma in an essential way. All right, so this gives some indication of how using the strongly indiscernible trees gives you some traction on some of the syntactic problems related to the tree property of the first kind. All right, so the next thing I'm going to talk about is amalgamation. Oh, and I should just mention that our motivation for this were certain questions in classification theory about a certain cardinal invariant, kappa in SCT. So this is a strict upper bound of the height of approximation to the tree property of the first kind, where maybe you have different formulas at each level. So, and Shelah asked as a question if the computation of this cardinal invariant reduces to computations in a single free variable, and this answers it in a certain special case. We also got one other sort of special case, but we don't know the answer to the question in general. All right, so now I want to talk about amalgamation. And to do that, I have to define another tree property notion. So this one's a little funny. In deference to traditional, I'll stick to the binary tree notation. So paths are consistent. This is the same situation. But we have this inconsistency with handedness notation. So what does this say? So it says, suppose I've got two incomparable elements. Eta is just going to extend the meet to the left. So I look at the meet of these two incomparables. Eta is going to extend it somewhere to the left. And nu extends the meet by 1 to the right. Then we get something inconsistent. OK, so what does this look like? So.
But isn't only incomparable path one stop with 0, one stop with 1?
Oh, you can't take it to be strongly indiscernible. So of course, if it were strongly indiscernible, then you'd be done. That would be the same. But you can't, in principle, assume that that happens. OK, so you start with a binary tree of tuples. Paths are consistent. And this is an instance of this inconsistency with handedness. So I look at these two nodes. Here's their meet. If this is eta, it extends the meet to the 0 and then goes somewhere else. This one extends the meet by 1 to the right. OK, this is inconsistent. Just by 1.
If you take any two incomparable nodes.
Yes. So
this is not true.
So the second one is really just the successor of the.
Yeah, this is.
Immediate successor.
Yeah. So
it has to be the successor.
So here.
So I see. One is the successor, one is the immediate successor.
Yeah. So
I didn't see that with definition.
yeah.
It was equality, 1%.
I didn't see equality.
Right. OK. So here two. Yeah. So, oh, like the definition?
Yes, definitely.
Oh, sure.
Oh, there's equality there.
Yeah. It's equals. Yeah.
What?
No, this is correct. Yes. OK, so look, here are two non-examples. So these purple guys might be consistent because, oh, whoops. So these might be consistent because this extends the meet by 2 and not just 1. These might be consistent because this guy goes somewhere to the left, but this goes by 2 to the right. So it really depends on the orientation too. OK, so this is a weird definition, maybe hard to motivate. But it turns out that it'll be equivalent to a very natural statement about amalgamation of types, which is perhaps surprising. OK, so what do we know? We know that simple theories are contained in the, there should be ins, sorry. So simple is contained in NSOP1, which is contained in NTP1, which equals SOP2. OK, so let me go back to simple theories for a moment. So in the paper, simplicity and stability in there's this really nice theorem. So yeah. So you say assume that there's a measurable cardinal somewhere. Then if you have the tree property of the first kind, then the independence theorem over model fails, both for forking and dividing. OK, so this is a nice theorem. Artem, on the way to proving an independence theorem for simple types in NTP2 theory, proves that you don't need the measurable. So actually, this is a theorem of ZFC. So in ZFC, if T has the tree property of the first kind, then the independence theorem over model fails. The measurable cardinal was just there to do indiscernible extraction. And if you do sort of moving the tree around a lot, you can get rid of that. And the thing we noticed is that actually this argument works for SOP1. OK, so this is a pretty mild improvement.
And independence is usual with what? Usual for dividing?
So forking and dividing is enough, but actually we get it for a stronger notion. We get it for co-error independence. And I'll state the theorem, because ultimately the reason this is interesting is that this turns out to be an equivalence. You get a strong failure of the independence theorem, and anytime you have a strong failure of that form, it had to come from SOP1. OK, so let me define some notions. So suppose I've got an invariant ternary relation on small subsets. So I'm going to define some notions of amalgamation of types. So maybe just to start with the simplest one, stationarity. So this is the familiar one for non-forking independence in stable theories. It says, suppose I've got two types, which I've got two elements which have the same type over a model. They're going to be free from this element C. Then actually they have the same type over the model and C. So there's a unique non-forking extension is what that says. OK, so that's a very natural thing. So now jump up to here. This says if I have two pairs of types, B0, C0, B1, C1, so they have the same type over the model, the BIs are free from the CIs, and the CIs are free from one another. Then I can find some guy which from C0's perspective looks like B0, from C1's perspective looks like B1, and they both satisfy the same types.
There should be a B1, C1. Yeah.
The B should
Well, I could also say equals B1, C1.
No, the middle.
No, the middle one, there should be a B1. Or should it?
No.
No, this is
C0.
this is right.
Oh, sorry. I'm sorry. Apologies.
Yeah. So maybe one way of saying this is that I let P of x, y be the type of B0, C0. Then what I'm saying is that P x C0 union P x C1 is consistent. This is equivalent. OK. And then independent amalgamation of types just drops the condition that these pairs of types have the same type over the model. So now C0 and C1 don't have to look anything alike. Yeah, so, oh, sorry. So this condition said that B0 and C0 have the same type over the model. And now I only insist that B0 and B1 have the same type of the model. I don't care what C0 and C1 look like.
So 2 is the usual amalgamation.
Yeah, so this is the usual statement of the independence theorem.
Hypothesis.
Yeah, that's right. OK.
So you don't claim that B is independent of something?
No, so we don't require that. But that's another stronger notion. So I would say it satisfies the independence theorem, if that's true. So, but these are the three notions we're looking at. We just want consistency, not just, it doesn't have to be independent. OK, so I'll define some independence notions. So this invariance independence just says that the type of A over BC can be extended to a global type Laskar invariant over C. And then we denote the dual by CI. So the dual just means that I look at the, A is free from B over C if and only if B is, the opposite over C with A. OK, and U is for ultrafilter. This is co-error independent. So the type of A over BC is finitely satisfiable in C. And its dual, well, ultrafilter independence is the same thing as co-error independent. So co-error independence should be error. So we denote its dual by H. So that's error independence. OK, so here's the theorem. The following are equivalent. Your theory doesn't have SOP1. And co-invariance independence satisfies weak independent amalgamation, or error independence satisfies weak independent amalgamation. So if you satisfy, if you have a weak independence theorem for one of these notions, then that implies that your theory is NSOP1. Something that, one interesting artifact of this proof is that these two things end up being equivalent, which I think is not, by itself, is not obvious from the outset as well.
True for any theory.
Yeah, any theory. No.
2 and 3 being equivalent.
Yeah, that's just true. OK. Great. OK, so one corollary of this is that we get a Kim-Pillay style criterion for NSOP1. So there's this beautiful theorem of Kim and Pillay that says that if you have an independence notion.
I have a question to about the theorem before, on the slide before.
Yeah.
So is one of the implications easy?
Yes. So if this satisfies weak independent amalgamation, then that implies this is a special case, because certainly if you're a cohere, then you're invariant. So this direction is easy, and the other two require some work. Yeah. Okay. So here's a corollary. So as I was mentioning, there's this theorem of Kim-Play that says that if you have an invariant independence notion which satisfies essentially these axioms together with local character, then you're simple, and that independence notion coincides with non-forking independence. So here we have to change some things. So one thing is that we have to drop local character, because if we had it, then we'd just get another criterion for simplicity. So we don't have local character here. The second thing is that we have to use this notion of strong finite character. And one way of thinking about this is saying syntactic character. It says that there's some formula in the type of an element which depends on B over M, such that any other guy which satisfies that formula will also depend. So dependence is always witnessed by a formula. And we know that this is necessary. So there are examples. Essentially, this is very close in spirit to Adler's notion of Mach simplicity. And there are examples, Mach simple examples, arbitrary high in the SOP hierarchy. So strong finite character is really important here. But we get this as a corollary. And
And the converse also holds, with a certain notion.
yeah, well, OK. So
The suitable notion of it.
yeah, so you have to say something silly for this. So if you define your independence notion to be like the disjunction of cohere independence and air dependence, then it will satisfy this for weak independent amalgamation. So if you put weak independent amalgamation here, you get a true statement. And it's equivalent if you say something kind of silly in number 5. So the reason we care about this is actually mostly just because we want to use this criterion to classify certain theories as NSOP 1. Okay.
How about the extension action?
Oh, so that's taken care of by existence over models. So for your theorem, I guess you need extension, but we only use this, sort of weak form of extension, which is existence over models. But that's where that shows up. All right.
So do we have the extension also?
No. So we only use extension in so you can think of existence over models as a kind of weak form of extension, right?
Because independence is a weak form?
Well, sorry, I'm saying existence over models you can think of as a very weak form of extension.
Yes, a little bit too weak somehow.
Well, yeah, sure. Yeah. All right. So this is the corollary, and I'll mention some applications. So one of them is that Nick Granger in his thesis looked at T infinity, which is the two-sorted theory of an infinite dimensional vector space over an algebraically closed field, equipped with the generic bilinear form. So basically, you have the field sort and a vector space sort, which is infinite dimensional, and you have this bilinear form connecting them. And Granger observed in his thesis that this isn't simple, which is fairly straightforward to show. But he defined this notion of gamma independence here, and showed that it satisfied existence, monotonicity, stationarity over models. And it's pretty easy to check from there that it also satisfies this strong finite character notion. And so it follows from our criterion that this is NSOP 1. Okay. So this is a new and very natural example of something which seemed intractable at the outset to show by hand that it was NSOP 1, but we can sort of import the results of Granger's thesis to get a really direct and easy proof that this is NSOP 1. Okay. Now, a second application is in a series of papers, Džamonja and Shelah showed that if you have an omega-free PAC field of characteristic 0, then there's a notion of independence. There are several notions of independence, in fact, but we only need one, satisfying strong finite character, existence, monotonicity, and independent amalgamation. And so these are NSOP 1. And moreover, it's a general fact that a PAC field is simple if and only if it's bounded, if and only if it has finitely many degree n extensions for every n. So if you're omega-free, then that means you're unsimple. So sorry, to say that you're an omega-free PAC field means that you have some elementary submodel such that the Galois group of that submodel is the free profinite group on countably many generators. Okay, so it's not bounded. And so this is an unsimple theory, which we now know is NSOP 1. And one
Non-simple.
Not you don't like unsimple?
Sounds like some horror film.
Complicated.
Okay. Not,
Undead.
yeah. Okay. Not simple. Okay. Okay. So and one last application that I wanted to mention is that there's this notion of a theory. I mean, sorry, there's this theory called T star FEQ. So this was, I think, introduced by Shelah and later studied by Shelah and Uzvietsov. And it was the canonical example of a theory which is not simple, but NSOP 1. Okay, so there were some doubts about whether or not the proof is correct. Ultimately, Gwyneth proved in her thesis that it's in TP1. It was not known if it was in NSOP 1. So we proved that, but we also proved something more general, which is that if you have a theory which is simple and it's obtained as a Frisé limit, satisfying the strong amalgamation property. So it doesn't have any algebraicity. And this is a really easy condition to verify. If you have a simple theory and you want it to not have any algebraicity, you can always just replace each point by an equivalence class. All right, then if you parameterize it in a natural way, so you add a new parameter variable to each one of the relations, and you can form a Frisé limit, which is like the parameterized version, then this will always give you something in NSOP1. And in particular, if the D rank of the theory is at least 2, then the parameterized version is not simple. Okay, and you actually need this. If you look at the parameterized version of the random graph, you get something simple back. Okay, so this is, we discovered after we did this that Bowdish had done essentially the same construction in a different setting, in a different, with different aims. But we ultimately got, this gives us a new stock of examples of NSOP1 theories. Okay, so I think I'm going to stop there.
Thank you very much.